All right, it's a little early, but I'm just going to get started just because I'm going to make an announcement and I'll post it so people hear it. So there's going to be a couple more times that I make the same announcement, but a seminar speaker is coming this Friday. He's an organic chemist, a good friend of mine actually, Jay Schneekloff. He's more, certainly a synthetic chemist. He's more what I would sort of perhaps, if you were to define him, I guess you might more likely to find him as what we call sort of a chemical biologist. So one of the things that he really likes to do is he doesn't necessarily develop too many new synthetic methods, like he doesn't develop new reactions per se, but one of the things that he does is he develops new techniques and strategies using chemistry to really solve problems in biology. And so some of the stuff that he's doing involves identifying new lead drug targets, for example. So he's big into sort of drug development, new strategies that you go into to sort of develop antivirals, and thus and such. So again, it's going to be Friday, basically 2:30 to 3:30. He's coming all the way out from Maryland, where he's been for the last few years. He's at about the same point in his career that I am. He's really doing some beautiful work. So again, I think it would be a great opportunity for you guys, especially those of you that are interested in sort of medicinal chemistry, to sort of see how synthetic chemistry can really be used and strategies can really be used, particularly like high throughput screening. So like how do you develop assays where you could perhaps screen tens of thousands or hundred thousands of molecules to identify lead targets for, say, a new biological enzyme that people think might be a good target for therapeutic development. So again, it's going to be posting things around. It's going to be 2:30 to 3:30 Friday in New Ingersoll. So I urge you guys to really consider it, specifically if you're sort of, which I know many of you are interested in medchem. All right, so today what we're going to do is we're going to transition into aromaticity. We talked a little bit about it yesterday, simply to do that one question, but I'll go into it a little bit more depth today. And much in the same way that carboxylic acids was kind of like two chapters, right? It was like derivatives of carboxylic acids and reactions of carboxylic acids, and it really should have been the same chapter. You could probably say the same thing about aromaticity, so I'm not going to like do chapter and then chapter. I'm just going to teach you guys about aromaticity. And so I'm going to sort of start the process, explain to you guys aromaticity, then I think what I'll do is I'll try to build upon some of the things that we did previously in terms of, for example, looking at resonance forms of aromatic systems, identifying what perhaps major resonance forms are available, which will hopefully build on some of the concepts that we saw in terms of enolates. Then we'll talk about sort of reactions, and hopefully, again, as we're going through these, we'll build upon a lot of the concepts and see, again, sort of hopefully be able to see why certain reactions take place the way that they do, perhaps even in a predictive way, right? I'll teach you guys stuff, but much of what I'll hopefully teach you will be stuff that you've seen already. Okay, so last week we sort of discussed the two molecules, right? Benzene, right? We started with this. We discussed benzene. We discussed cyclobutadiene, and we discussed how this is a molecule that's aromatic. All right, we discussed how this is a molecule that we would call anti-aromatic. This is unstable, and this is stable, right? So aromaticity is often tied very directly into stability. So there's a lot of reactions that we'll often see run, right, where the product that's formed is often driven by the formation of an aromatic compound, and then again, based upon energetics, that will be a thermodynamic driving force behind, for example, reactions. And what we sort of discussed yesterday was how this molecule sort of represents 4n plus 2, right, where n equals 1, so this total thing is 6 electrons, right, so this is 6 electrons in total, so 4n plus 2 is sort of aromatic, and then if we have 4n, right, that's anti-aromatic. So again, to memorize the equation per se, you really need to memorize this 4n plus 2. I don't understand why that's something that we need to memorize per se. Just, I think you guys because you guys have seen benzene a lot, right? You might, without even really thinking about it, you see benzene and you see this compound that you've been seeing for probably the last year that's been attributed to stability, right? We'll often talk about reactions on alkenes, and we'll throw benzene on there, and the chemistry won't work with the benzene for these reasons. And so again, I think it's just best to recognize that benzene is aromatic. Add 2 electrons to a system like this, it's going to become anti-aromatic. Add another 2, it goes back to aromatic, and so on and so forth. So whether you memorize that equation or not, is up to you. It's a fairly silly equation, I guess. But again, one that sort of at least makes sense of this. So last week we were talking about why this is, and we don't really discuss molecular orbital theory in too much depth in this course. We discuss it a little bit in terms of Diels-Alder chemistry, where I think it becomes relevant to chemistry. You can sort of use molecular orbital theory in a way, or start looking at the molecular orbitals of aromatic systems to perhaps appreciate aromaticity, but sometimes I'm not sure that it really would mean too much to you guys, but I'll just show it to you so that you can sort of see how this is the case. So in the case of benzene, the molecular orbital of the system, right, is such where we have our 6 electrons. They're all in the pi orbitals. Okay, and again, there's this sort of, if you want to call it hybridization or whatever, but they form to create these molecular orbitals. And again, one of the things that we'll see from time to time, just have the symmetry. I'm never going to ask you to draw this per se, but I'll just tell you this is what the math tends to lead to in these cases, is this molecular orbital. And if you sort of look at this, this is something that you see quite common, this sort of symmetry to this, right? You have sort of for every orbital going in one direction, there's sort of an equal and opposite orbital going in the other direction. But again, the important point is that as you fill this diagram, right, we're going to fill it 2 at a time. This is similar to if we're filling, for example, hydrogen in these. We put all the 6 electrons in here. Right, we see that what we've done is we've sort of filled all of the sort of more stable orbitals. Right? Now, how to get to a structure like this, again, I wouldn't necessarily expect you guys to see it, but sometimes it can be helpful to look at what they call frost diagrams, which is a system where you don't understand exactly how it works per se, but you take a look at the structure of that molecule. They call it a frost circle, I guess. But again, you sort of look at the molecule like this, and you can sort of see that you've got this would correspond to this one, these 2 would correspond to these 2, these 2 would correspond to these 2, this one would correspond to this one, so there's a similarity. So what this means, again, I'm not entirely sure, but it's at least a way that you could, in principle, predict, I guess, what a molecular orbital might look like in these compounds. But again, I'm not too concerned about you guys being able to draw molecular orbitals. But again, here it is. Here's the sort of molecular orbital diagram of these. And then again, you do the same thing with, say, for example, cyclobutadiene. Right? In this case, there's going to be the 4 orbitals. Right? And again, if I start thinking about that as, why do you do it this way? I don't really know. But that's the sort of frost circle. It ends up looking like this, right? And again, as we start to fill these, right, we fill them 2 at a time, but much in the same way that you've probably seen in general chemistry, you sort of go across, right, and what you see is in this case you end up having these sort of unpaired electrons, right, and so in this case you can clearly see that there's not necessarily a stabilizing factor in this. You end up having electrons that are unpaired, and again, perhaps this helps explain further the differences between these 2. Now we can take it the next step and we can begin to draw, say for example, an 8-electron system, which based upon the math, you would assume would be anti-aromatic, right? If we have a molecule like this, right, we could probably draw it on the side. Frost circle again, I'm going to fill it. Again, there's 8 electrons in there, so it's going to be 1, 2, 3, 4, 6, 7, 8. Again, so you have this sort of unpaired electron again, and you can imagine if we went ahead and we did the next one, which would be this molecule here. You see the point, right? Now I'm going to have one, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7. Sorry, 10, right? So now if we start to fill this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So we've got that sort of fill again where, again, you see sort of at least some symmetry to the benzene, right? Where it's sort of symmetric here and everything is sort of stabilized again. So again, I don't really care about having you guys draw this, but I'm just showing you there is this sort of molecular orbital explanation behind it, and you can sort of keep going on and on and on, right? So as I said, I don't care about this, and you guys being able to do this, but what do I care about aromaticity is, again, sort of chemistry. So once you guys can, I expect you guys to be able to recognize when molecules are aromatic or when they are anti-aromatic. That's certainly something that I do want you to do, but drawing molecular orbitals of them probably is not going to be that important to me. For the most part, what we're going to be dealing with in this course is reactions of benzene, right? And as we start to talk about chemistry with benzene, we are going to begin to see chemistry on these that takes place at different positions, right? So if you have, say, for example, an electrophile reacting with this structure, right? We can at least in principle draw a mechanism analogous to what we've seen with alkenes. Okay? So when that reacts, you have that sort of carbocation cation there, right? And then what's generally going to happen, right, is that you have this drive in the reverse this drive of an elimination process with, say, for example, a counter ion, right? So if I have some leaving group there, that leaving group could then react and regenerate the compound. So you can do chemistry on aromatic groups, and we'll show you guys about some of this. This would be sort of like the electrophile reacting with this. And the other thing that we'll see from time to time is the reverse. And so we'll see examples where we have, this is called sort of electrophilic aromatic substitution. We also have nucleophilic aromatic substitution. Now, when have you guys seen alkenes? So alkenes behaving as nucleophiles, we saw that last semester, right? We've also seen alkenes behave, sorry, as nucleophiles, we saw it a lot last semester. Where have we seen alkenes behaving as electrophiles? Right, so instances where we have alpha-beta unsaturated groups. And so as you might imagine, it's going to be the same thing for this as well. So if we have an alpha-beta unsaturated, say, for example, an acyl group there, now what we've done, right, is we've embedded within that system, right, an alpha-beta unsaturated alkene. Right? And so in this case, this is going to be nucleophilic aromatic substitution. Treat this with, say, for example, a nucleophile. Again, we'll go into a little bit more depth in this later on, but I'm just trying to give you guys an overview of what we're going to need to know for this class. For aromaticity, all right, there's going to be a 1,4 addition. As we'll see later on, you can also do a 1,6 addition, but I'm just going to try to keep it simple for now. Okay? But the issue here, and we'll get to this later on, is then what will we do at this point, right? Like, we got to redrive aromaticity, right? So we're going to want to redrive aromaticity, and so what will generally happen here is it will kick back off a nucleophile, right? So how would we make this perhaps a productive reaction? Instead of it kicking off the nucleophile, right, we'd want it to kick off something else, right, because it's going to drive the reversibility, right? So we'll talk about this later, but what you want to generally have is some type of a leaving group there as well, okay? And so if that's the case, so it's a little bit more than simply having an electron withdrawing group there. It's going to be having an electron withdrawing group and then some type of a good leaving group. And again, we'll discuss this in a little bit more depth as we move on. But in this case, what you're going to see now is really an exchange, right? We're exchanging, say, for example, something that we consider a good leaving group, something like, say, for example, a halogen, right? So maybe a chloride is there, maybe a bromide is there. We'll see there's some other ones like nitrogen leaving groups that we'll see on occasion. But really, this is going to be the sort of two classes of reactions that we're going to sort of discuss. And so much of what I'm going to start talking about in terms of what makes molecules aromatic is really going to help us explain, for example, when reactions would, say, for example, react at specific positions and when they wouldn't react at specific positions. So a lot of what we're going to discuss today is really going to be looking at aromatic compounds, recognizing where these molecules are, say, for example, electrophilic and more electrophilic, right? Because we have lots of potential carbons around here. They could be electrophiles, but what we'll see is that you could react there, or perhaps there, but you're never going to react there. And then again, depending upon the substitutions, right, on our benzene groups, there may be some regiochemical selectivity there as well. So this is just the overview. This is sort of where we're going with this chapter, just to sort of keep a big picture on what we're doing. So last week, going back to what makes a molecule aromatic, we'll get back to reactions, but that's just to sort of keep in mind as we're moving forward, as we're talking about these things. This is where we're heading. There's still that basic question: how do we know whether molecules are aromatic or not? And there is certainly this idea of 4n plus 2 that we discussed. But I think it's important to recognize that there are many aromatic systems that perhaps aren't so simple as benzene, right? That might look a little bit more difficult. We discussed one of them last week, right? And that's furan. Right? And so what makes this sort of 4n plus 2 drive is that you need 4n plus 2 electrons within a sort of, whether you want to call it like a closed ring of pi systems. And so, as we discussed last week, if you look at a molecule like furan, right, we only see these two double bonds, right, but there are an extra couple electrons in here, and they end up being in the oxygen. In fact, there's 2 electrons in that oxygen. Okay? But what happens is, to reach aromaticity, those lone pairs are going to want to exist in a p orbital, right? If we need a ring of p orbitals in the system, want this ring of p orbitals, what's going to happen is we'll have that oxygen will change its hybridization, right? Just looking at it maybe a week ago, you might have looked at that oxygen and said, okay, that oxygen is sp3 hybridized, right? You might say, everything's going to want to get as far away from one another as possible. Right? But because aromaticity is such a major stabilizing force, what's going to happen is this oxygen is going to rehybridize to basically put one of those lone pairs into a p orbital, right? So this oxygen is now sp2 hybridized. It becomes sp2 hybridized. And again, what that's going to lead to now is an additional couple electrons in a p orbital. So now what we have is that closed loop, right? And that makes it in total now aromatic, right? Because there's 1, 2, 3, 4, 5, 6. So this is what you'll see sometimes in aromatic systems. We can see the same type of things in terms of stabilizing groups. Okay, so this molecule, as I've shown right here, right, is not aromatic, right? But as it turns out, this molecule can be deprotonated, right, very readily. Right? So if you take this molecule, you treat it with base, right? These protons, which on the surface might not look all that acidic, right, are actually fairly acidic because the product that you generate in this reaction now has that lone pair. You've allowed down the lone pair, which can now hybridize into p orbital. The same way as we discussed before. And this molecule is in fact aromatic. So see if I have the pK values here, which I believe I wrote down. Somebody say 16? Sounds about right. Yeah, so what would it normally be? What would say, for example, what would you expect? What do you guys reading ahead? All right, good. So a molecule like that is perhaps going to be an allyl group. You might stabilize a little bit, but the pK is probably, yeah, maybe 40 at a second allyl group. Maybe it's gone down a little bit from there, but it's not going to be dramatic. But yeah, just like you say, if the pK of this, if we just approximated it somewhere in the 40 range, right, a molecule that's now cyclic, right, actually has a pKa, and I'll take their word for it, is about 16, which makes sense. And I believe you can actually protonate these with things like p-butoxide, which would make sense then, right? P-butoxide, which has a pK of about 18 or so, can now be protonated. In fact, this is a ligand that people often use in, for example, metals, right, because it can bind really well in this sort of form. Okay? Likewise, so these are sort of anions. There are also instances where you can generate cation leaving groups pretty well, right? So let's say, for example, you had a molecule like let's say, for example, you had that cyclopropyl cation, cyclopropyl prophenyl chlorocation, right? That chloride can now be a very, very good leaving group. Why? You might not expect it to. You might expect a lot of ring strain in there, but in this case, what's going to happen, right, is now you've got a cation there. Okay. So again, back to our 4n plus 2, if you will, right? If n equals 0, right, and that's 2. So this is aromatic, right? And so actually, Tristan Lambert at Columbia does a lot of chemistry that's really driven by the formation of, say, for example, things such as these cyclopropyl carbocations. But again, if we're to sort of draw this and really think about it, right, we have an empty p orbital there. So it's a closed loop, and in total, right, it's got those sort of 2 electrons to it. An instance closer to home in our group, one of the things that we work with a lot is molecules called tropolones, or this is a tropone. This is a tropone. We work with molecules that have more hydroxys on it. As it turns out, this molecule is also aromatic. Why is that molecule aromatic? And how is that molecule aromatic? If we can look at the resonance form, right? So if we take a look at the resonance form of this molecule, and we simply push those electrons up into the oxygen, Right? Now what we have is a new resonance form. Right? Where we have that sort of carbocation there. The fact that now you have this carbocation there, it can be stabilized, right, throughout this whole system. Right? So if we think about this. Right? You've got that sort of loop of p orbitals. Right? And those p orbitals are that sort of 7 carbons in total, but in those 7 carbons there are in fact 6 electrons. So it's that exact same count as, say, for example, benzene. Now, one of the things that's interesting about this is that these molecules, what impact do you think that that's going to have on, say, for example, the nucleophilicity, the Lewis basicity of that oxygen? Be much better, right? Because it's going to exist in many ways like this negatively charged oxygen, right? It's going to want to push those electrons onto that oxygen, which is going to put more charge there, which is going to make it want to react. This is actually one of the things in our group. I'll just tell you really quickly about the class of molecules that we've been working on and how this is related to it. Up in our lab upstairs, we work on a class of these molecules called alpha hydroxytropin. Once again, they have 3 oxygens in a row, so it's basically a tropanoid with 3 oxygens in a row. Turns out that these are extremely acidic. Well, not extremely acidic. They're not actually overly acidic, but they are right in the kind of sweet spot where the pK values of these are about 5 and 7. So pK of about 5. Okay, and the other pK is about 7. Huh? Because once you deprotonate the first one. Yeah, they're identical, right? The point is that it's pK1 and pK2. So once, yeah, all right, once already deprotonated. Probably did that poorly. That's probably not the best way to draw that. But once already deprotonated, yeah, thanks. So the point is that monoanionic form of this, if one's deprotonated, it's going to have a negative charge on it. That's kind of what I meant to say. So when there's a negative charge on it, to just deprotonate it once, as long as your pK is, say, for example, above 5, it'll be deprotonated once. If your pK is above 7, then it's going to actually be deprotonated twice. So it'll be dianionic. Right? What's physiological pH? 7.5-ish. Right? So this molecule will actually be heavily dianionic at physiological pH. Those oxygens. And kind of the cool thing about this, right, is that you could also put a third negative oxygen on there because of the right. So you'll have that carbocation there. One of the ways that we'll often draw this is to sort of illustrate that you see this is benzene, right, a big circle, but now we're going to put a big positive charge in the middle, so sometimes we'll draw this. Right, so it's kind of interesting about these molecules that physical pH, what they have is these 3 highly negatively charged oxygens, which are all sitting next to each other, and it turns out there's a lot of enzymes that have sort of 2 metals in them, and these will sort of bind in this kind of fashion. So they're really good inhibitors of a variety of different enzymes. So here's just an example of where that tropylium stabilization, or where that aromaticity of the tropylone actually makes that middle oxygen also Lewis basic in nature. It's going to depend upon, well, they'd be fully shared in this structure. Yeah, I mean, the middle one might be a little bit less, but yeah, it's, All right, so anyways, you'll also see several other examples of aromatic systems, right? So we've seen it all sort of cyclical, right, where it's just one giant cycle. But you'll also see sort of bicyclic aromatics. So this is a molecule called naphthalene. Okay, so naphthalene is, I think, the you generally have in like small balls. You guys probably worked with naphthalene in the past. You'll sort of see that you got the benzene over here, but there's also another 4 electrons over here. This exists as one big p orbital that's got 10 electrons in it, right? So if we sort of think about this, right, this exists as one big closed p orbital system, even though there's that bond there. So things like naphthalene are aromatic not because it's a benzene sitting over there, but it's aromatic more so. It's aromatic because, in fact, you have in the system actually 10 electrons, right? And 10 electrons, again, if we go back to the 4n plus 2, right? N equals 2, right? And it's 10. Or we can think about it the way that I was trying to tell you guys, right? Benzene is 6. Aromatic. 8, not aromatic. 10, back to being aromatic again, right? So this is an example of naphthalene. Anthracene is another one that we sometimes see. It can even go beyond 2, right? So here's a molecule, anthracene. Right? You can see that that's a system that actually has 14 electrons to it, okay? Probably, yeah, that'd probably be the case. Well, right, so all of your p orbitals, so we'll get to that in a second. So all the p orbitals have to be, right, in the same plane. There has to be that conjugation. So if you disrupt that ability of all the p orbitals to align, which is the question that's being asked, that's going to be a situation there. Okay, when we get to nucleic acids, we're going to see another series of molecules. Again, it's important to recognize the sort of shape of these.
But you said the last one is aromatic also?
6, 7, 8, 9, 10, 11, 12, 13, 14. 3. Yeah, no problem. All right, so another place where you guys will see later on in the semester, I'm going to make 2 points here. Here's a molecule, or here's the base pair of adenine, which is a nucleic acid. We'll see this later on, but for now we'll just discuss in terms of aromaticity. Right, if you were to look at this molecule, right, you may look at this molecule and it might not be all that obvious, right, that it's aromatic. Right? Because at the surface, right, you don't really see perhaps all of the, it doesn't seem like a whole bunch of alkenes within a pi system. It becomes a little bit more complicated than that, right? Because what you have is, well, what you'll notice is you have that lone pair over there, right? And this is an amide, right? So you can imagine there's a lone pair here, right? What's that? This one right here? There is a lone pair there, but we'll get to that in a second. That's not going to necessarily be relevant in the system, right? Because that lone pair is not taking place in the p orbital. Same with this one up here. That lone pair, we're not going to worry about these two, right? Because they're not involved in that. Certainly there's a lone pair here that might be tied back into this, but we can talk about that later. But I want to make a point here. But there's again the empty p orbital here. So on the surface, adenine might not look aromatic, but in fact it is, and it's known that it planarizes, right? So let me just draw the resonance form here, just to make it easier, right? So now we've got a resonance form there, so now it becomes an additional pi system in this, right? So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So if we were to draw this molecule, right, on its side, right, we would have we have a molecule that looks something like that, right? And so we have a closed loop of 10 electrons. And so, and again, 10 electrons is aromatic. And so, in fact, these molecules, when we talk about this, when we get to nucleic acids, this molecule is very flat, right? Because, as we sort of stated earlier, you want all those p orbitals to be able to sort of overlap, form that system, and the way that it's going to happen, right, is if it's fully planar. Right? So this is adenine, it's going to be fully planar. I want to ask another question though, that maybe you guys are starting to think, right? I have drawn adenine at least on its surface as a carbonyl. So here's adenine, right? Here's how adenine exists, right? But there's this tautomeric form of it, right? And this tautomeric form, right, has the double bond already set up. It doesn't even need to bother with this resonance form, yeah. There's 2 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You're probably not counting these 2. You missed those 2. Yeah, you probably missed those 2. Were those the 2 you missed? Yeah. Yeah, so those 2. It's the same with like, yeah. Okay, so but here's the question, right? Here's the tautomeric form of this. This is actually a question that came up back when I was in graduate school that I think reinforces this thing that we are seeing time and time again. And here's a tautomeric form of this molecule. In fact, as we'll see later on, if that's a nitrogen, that will be NH3 and it will be in this form here. But in terms of adenine, it exists as the sort of carbonyl. Right? Doesn't that seem kind of weird? Maybe? Right? Why? This sort of reinforces something that we're seeing time and time again. Why do you think we draw this? Why do you think it exists as a carbonyl rather than this? Yeah, because this is just one of these things we see. Carbon-oxygen double bonds. This just reinforces is that idea of carbon-oxygen double bonds being stable, right? Being the stabilizing factor. Again, we see it in the enol keto tautomeric form. Why is it the keto rather than enol? Again, it's that carbonyl. Why is it that synthesizing a hydrate, right, 2 OHs coming out, you know, having water, why can't water add into a carbonyl and exist as 2 OHs, right? It's because the carbonyl is important. Why are hemiacetals rarely things that we see as stabilizing factors, although we do sometimes see it in intermolecular case, or intra, excuse me, we almost never see it inter. So again, that's just another reinforcement of this idea of carbonyls. Okay, so I expect you guys to be able to recognize when compounds are aromatic, probably for not this upcoming quiz, but probably for the following quiz. There'll probably be a question that'll come up. Is this molecule aromatic? Why? So you'll be expected to recognize that. But moving on to the chemistry, right, I think it's important to recognize that there become some complications that actually aren't all that much complications for the synthetic chemist. They actually become a versatility associated with aromatic groups so that we can put lots of different groups on them, right? And so, as we talked about earlier, here's a molecule benzene with a methyl group on this is actually called toluene. You guys might have heard of toluene. All right, so this is toluene. And when we begin to start talking about chemistry of benzene, and we start thinking about reacting these molecules with, say, for example, electrophiles, there's going to be a few different positions, really multiple positions on this ring that we can go after. In the case, as I've drawn here, this molecule is symmetric, but it really could attack these positions, which are the same, these positions, or this position here. Right? And so, okay, so there's really three potential regioisomers, at least this is drawn here, that could form. And as we'll sort of discuss, there's some selectivity associated with this, so they're not all going to form necessarily, and we'll sort of explain why. But it's important to be able to recognize, and we'll sort of get into this, which positions they would be most nucleophilic, right? So the first thing I just want to get into is some nomenclature. I hate nomenclature, but it's important that we discuss nomenclature here, at least for the sake of this. But the sort of proximity, the sort of the two groups, when there's two groups on a ring, or when you're referring to two groups on a ring, we'll give different names associated with them, so we've sort of got to know them. And these are going to be ortho, meta, and para. How you're going to sort of remember these, I don't know, maybe you know Latin or something like that, or whatever they're associated with. Maybe para is like across to you guys or something like that. But again, you just sort of have to get a name or a way to sort of know them. And when we draw them, oftentimes we'll sort of have these subscripts O and P. And usually, sometimes if you have like a go-to molecule that will sort of help you remember them, the one that's always used for me is para-toluene sulfonic acid. All right, this is just a reagent that we use a lot upstairs, and so you'll often see it. Para-toluene sulfonic acid. And so this is like one of the things that's sort of like my benchmark, because we use this all the time. And or another one would be metachloro, MCPBA. Right, so you guys used MCPBA. So MCPBA stands for metachloro parabenzoic acid, so MCPBA. So the M there stands for meta, the P here stands for para. And so again, I think once you start seeing some of these reagents and knowing the structures of them, that's how I remember them, is just through the reagents. But this time point, you may just want to sort of memorize them, even if those will be short-term memorizations. But from a regioselectivity standpoint, it turns out that aromatic reactions can be fairly regioselective, so they can be selective for specific points on these rings, and I think it's important to recognize and be able to predict where the favored positions would be. And one of the things that I like to do, again, it's always best, you could try to like memorize it, right? So the book will tell you, oh, a donor will be an ortho-para director, right? Something that's electron drawing might be a meta director or something like that. And I never really liked these that much. I mean, you can certainly try to memorize them, but as you try to memorize things, it just becomes more and more memorized. So I think that if you sort of want to understand it, maybe you'll eventually memorize it without even realizing you memorized it. But one of the things that I like to sort of teach people, what's that, Karen? Oh, no, I was talking about reactivity. Yeah, so know these names. memorize these names. What I was saying is I'm going to show you guys how to rationalize selectivity. So that's what I was saying. Don't memorize the regioselectivity. Unfortunately, we've got to memorize these at least for a time because those are just the names. And I'm sure if maybe somebody in here, does anybody know Latin? There's probably Latin associated with it or something. So if you took Latin, maybe you'll sort of understand what they mean. But there's unfortunately no Zameside epithet that can help you guys that I can think of. But if somebody comes up with one, you can share it with the class. I'm sure they'll all appreciate it. Now, one of the things to recognize, again, we discussed this a little bit earlier, right? That oftentimes where the delta positive or the delta negative is, there's sort of this delta positive, delta negative, delta positive, delta negative sort of pattern, right, that exists. And you can begin to see that at least a little bit with aromatic compounds, right? So I can, in principle, push electrons sort of one of two ways, for example, on this alkene, right? And again, these are just to sort of look at the resonance forms of these molecules. Right? Whereas over here, and again, when you look at these two resonance forms, I think most of you guys can probably predict which one you'd rather push the electrons, right? Which way would we rather push them? All right, I'm seeing a bunch of people say this one, right? It's the right one. So when we're sort of looking at that single electron being moved, right? We can probably, if I just showed you these two guys, it seems like you guys know, again, it would be this one. Why? Right, inductive effect, hyperconjugation, the more substituted, right? The methyl group is helping stabilize that more, right? But in these systems, what we often also have, because of this sort of conjugated system, is that you can move these charges onto other bonds in the system as well. And so depending upon whether we're looking for the delta positive or the delta negative, for the sake of trying to identify, for example, the delta minus in this standpoint, because this is what we were talking about earlier, right? It being a nucleophile, we'll look at where the delta minuses are, and then we should be able to figure out where the delta positives are, because those will just be everywhere else. So this, at least in terms of this resonance form, right? Here's one position. Here's one resonance form. Right, so we can push that negative charge there. We can also push that negative charge on that carbon. Room. Right, and so what we have here is really the three positions that we could put that negative charge. So as is drawn, right, these would be the sort of resonance, if we wanted to have a delta minus here, delta minus here, delta plus would be everywhere else, delta plus, right? So in principle, again, we'll discuss why this is probably not the case, but in principle, by looking at these different resonance forms, this would be the illustration at least, right, that would explain the delta minuses here and the delta positives everywhere else. But if we look at the one that's sort of, we already decided we don't like this one, right, we like pushing it this way, let's take a look at these, right? We can push that negative charge here. Right, we have the negative charge here. So at least in this resonance form, right, which you sort of already agreed to is kind of like the better of the two, we don't have this, right, but what we have, right, is delta minus here, delta plus here, delta minus here, delta minus here, delta positive here. Okay. And again, if we didn't right at the beginning, I think you guys kind of hit it on the head right off the bat, just because of the way that we pushed it, and you guys said, well, I like this one better, but you got to look at the combination of all of them, right? It's like we can put that positive charge to that position. We can hang it out there for all these different resonance forms. We can't get that delta positive back there, right? So once in an aromatic system, once you go one direction, and you sort of separate it because of this sort of positive or negative charge, you can't actually, it's very difficult to move the negative charge or the positive charge anywhere other than one of those bonds, right? And so again, as we evaluate these two options, we recognize that this isn't what's happening, and this more likely is what's happening. Does anything stand up? Okay. So as we're looking at this resonance form here, if you will, when we go back to that basic electrophilic aromatic substitution reaction that we saw earlier, this explains which carbons are the best nucleophiles, right? The ones that bear the best delta negative are the ones that are going to most likely be the carbons that we would attack from, okay? So on this molecule that we've shown here, right? Oops, I erased all the possibilities. We can either attack from that carbon and get this one. We can attack from this carbon, which would actually be the same thing, just flip the other way. Or the other option would be this one here. So when you're treating a benzene group with an electrophile, we'll talk about the specific reactions later on, but kind of what I want to show you guys is that there's this regioselectivity that when you take a benzene group, you can in fact treat it, right, with an electrophile. And if there's a donor, there's a donating group, right, it's going to direct it here or here, right? And so this would be ortho, right? This is ortho. And this is para. So I know a lot of you guys will start saying, oh, it's an ortho-para director or it's a meta-director. Again, it's fine if you know, once you get it down, it might just sort of make sense, and you don't have to memorize it. But again, I like to sort of have you guys sort of understand the basics, just in case you're in an exam or wherever you can't quite remember what you would try to memorize. So at least you have that foundation. You can sort of figure it out on your own. Okay, so this would be a donor group. What are some other examples of donor groups? Do you think? So the methyl group's a donor group. Why? It's donating, well, yeah, but if we think maybe about this reason, right? It's stabilizing the positive charge. So in a way, the donor group is kind of going to be a group that's going to help stabilize that positive charge. So what might be another group that might be here that would be really good at stabilizing the positive charge? Maybe an oxygen? What were you going to say? No. Yeah, no. You have to show me. No. Yeah, show me. No, but no. So there might be specific cases where maybe that's the case, but I'm not sure. But in this case, anything that's going to help stabilize, for example, that positive charge.
I know what you're talking about as well. It depends on whether you have the oxygen after the carbon. Like if you have the OR attached to the thing, then it's going.
Got it. All right. Yeah. So, but the point is that something with an oxygen there, right? Right. So we'll get back to. So that's what you're saying. If it's, say, for example, an ester where this is an O carbon double bond, right? So I guess that would make sense. But yeah, something with an oxygen here, right? So an ether, maybe a nitrogen, right? Something that has that other set of electrons could, right, donate. One of the weird ones, in a way, is what else has lone pairs that could donate in? Right? So we've got oxygen, we've got nitrogen, maybe sulfur could probably donate in, right? But what else has lone pairs? What's that? Phosphorus. The halogens, right? And this is one of the interesting things, right? The halogens are kind of one of those weird ones because they can do the same thing. So halogens we will also see as ortho-para directors. So anytime that you could stabilize this cation, right? So if I just put X here, or let's just say X kind of already implies it. Let's say Y. just call it a Y. That's a horrible Y. That's also not a very good looking Y. Let's go Z. It's not my best drawing day, right? We'll just call it Z for now. If Z equals, say, for example, a carbon, like an alkyl, so like a carbon, say like a methyl group or an ethyl group or a butyl group, because I don't want to just say carbon because we'll discuss some of these cases in which case it wouldn't do this. But if you have something like this, if you have an ether or an ester where the oxygen is connected to that, I guess. Halogens, amines. But again, we're talking about what's directly attached to it. So there's an oxygen there. Basically anything that can either stabilize through inductive stabilization, so something would have like a tertiary group there. Sulfur. Really just anything with lone pairs or alkyl groups. Okay. Now, not all groups are necessarily going to be what we would call donors, right? And so when we're saying donors, kind of what we're referring to again is things that can help stabilize that positive charge. What about groups that might, yeah?
I have a question about the halogens.
Mm-hmm.
Aren't they producing?
So this is why they're a little bit weird, yeah. So halogens, the resonance sort of explains them. They actually don't, I never really teach this that much, but like, if you were going to have a donor in this system, and you treated this with an electrophile, the majority of these would accelerate that reaction if you're treating them with an electrophile. The halogens don't. But they still direct in that direction. They still direct. Yes. They're weakly deactivating. And what that means is that they make the reaction a little bit slower. But they're still ortho-paradonors. Yes. That's why I was saying those ones are a little bit weird. And again, you can explain it because they do have those lone pairs. But you're right, it's kind of weird because it's like, well, they're electron withdrawing. And they behave that way in terms of the effect on the rate of the reaction, but they don't behave that way in terms of the regioselectivity. Okay, so I wasn't really going to discuss rates because it's kind of, I don't really think it's too important, but if it comes to it, we can. So I'm more curious about regioselectivity, okay? All right, so now we discussed all these cases where at least you could stabilize this carbocation, and maybe what you'll say is, oh, a halogen won't stabilize that carbocation all that well. Maybe it'll destabilize it more, but at least through resonance, you can imagine that resonance form, and certainly halogens give you ortho-paradirecting. And so for the sake of this course, I would just think about them as donating into that group. Okay, so this is a donor. The next question becomes, what about groups that would sort of lead to the opposite, right, regioselectivity? So we'll just start with the ester because that was the one that came up earlier. Let's discuss the ester. Okay, so here's the ester. Here's the other ester, right? This is, the ester where the carbons bonded to it. So again, I didn't want to confuse this too much. But again, if we did the same thing that we did before, we look at an ester group there, at least where the carbonyl, right, is directly attached to this group here, right? We have two resonance forms. Again, this is analogous to what we just did. Now we have two alternatives. I've just drawn the same thing here, but now instead of having something that, say, for example, stabilizes the cation, now I've got things that can actually stabilize the negative charge. Right? We've got an ester, right? And so when we look at these two, right, you can make arguments towards one or you can make arguments towards the other, right? I think this is one of those situations where your intuition might say, well, what's the difference, right? This is a tertiary carbocation, right? So it's still going to want to be the tertiary carbocation, because that might be your intuition. That's fine. And in fact, at one point, somebody a long time ago probably expected that that would do that. Maybe. I don't know. But there's something else going on here, right? What else can it do? Right? So there's two factors here. First of all, you've got a delta positive there, and this goes back to what we talked about. We were talking about alpha beta unsaturated ketones and esters, right? And where that delta positive is. We've got a delta positive right next to that carbonyl. So it's not really your typical inductive stabilizing group, right? Because you've got it's a withdrawing group. So it's a withdrawing group right next to a cation. Meanwhile, having that withdrawing group there is great, right? Why? What's that? Yeah, absolutely. But even more so, what can we draw? The resonance form, right? So we can draw, in fact, a resonance form. All right, so we can put that negative charge there. So in this case, this one, right, is going to be better. Right? And so I'm not going to go through all the ones over here, but what we'll so I'll just erase this for board space. But you can see that when you have a group that can stabilize like this, right, we're actually going to get the opposite type of donation, right? So let's look at the different resonance forms here. So what do you guys notice? That now we put that negative charge where? We've got it, this carbon and this carbon. So in this case, right, here's our delta minus. Here's our delta minus. Maybe in some cases this carbon could attack, but again, it's already substituted, so we would have to have that attack and something else happen here. So really the two that we care about are really these two positions here. Right? And so in cases in which case you can stabilize like this through resonance, right? You're going to have a different type of regioselectivity. You okay? It is kind of brutal. So in cases where we have Z equals, say, for example, a carbonyl, so C, right? When we treat this with an electrophile, we're going to get different regioselectivity. It's going to be meta. Okay? So what are some other examples you think of groups that we know of that might also direct meta? This is why it's usually best, like the question was coming up earlier about halogens and how halogens are withdrawing. But when you think about regioselectivity, it's really the resonance that ends up trumping in these cases. Say that again? An enamine might? Sure. Well, an enamine... No. Well, let me think about this. So electron would, because it would have to stabilize through withdrawing, right? So if we have, let's just look at, for example, this resonance form here. There may be an enamine that stabilizes it, but not the one that I'm at least thinking of. So we want something that could withdraw. And so an enamine, right, isn't necessarily going to stabilize that, right? Like you can push the electrons maybe onto this carbon, but that's, you know, that's not really going to help stabilize it too much. So enamines, I don't think so, probably not, but you could certainly draw resonance forms. So there may be something to them, but I don't think so. But maybe, I don't know. We'll look it up and try to figure that out. What else though? There's another nitrogen-containing group that we see as stabilizing. Yeah. Cyanide. Right? Cyano, right? Is it cyano? What do you guys think? Can the cyano stabilize that? Can you draw a resonance form? That seems like a good resonance form? Absolutely. Look at that. You push that negative charge up into nitrogen. So to go back to the question about the enamines, there's also the resonance form, but you're kind of pushing it onto another carbon. I'm going to look into that because I don't know. But certainly this is a case where you're pushing it onto a nitrogen, right? We've seen this in the past. So let's say cyanos, right? That would be a good one. What else? Is that? An amide, right? So amides would fall under the sort of carbonyl, right? So pretty much anything, somebody brought up amides, so pretty much anything that has a carbonyl here, right? So an amide, an ester, a ketone, right? Right, those are all going to have that effect. So it's carbonyl, let's just classify those as carbonyl directly attached. But certainly an amide would fall in that class. Or some other groups that could resonance stabilize. What? Nitro? What do you guys think? Nitro? What do you guys think of the nitro? Nitro's fantastic, yeah. I got some of that oxygen? Absolutely. Right. Okay. What else? Is there another one that we haven't? Some nitros. All right, what else? We've done nitrogen. Sulfonyl, yeah. So anything, and we'll sort of something like that, certainly. Or even maybe that, right, depending on which oxidation state we're at. So again, the sulfoxide or the sulfonyl, certainly the sulfonyl is going to be better, right? Right, so there's a whole bunch, right? We can think about a lot of these, right? What about a phosphorus, right? What about something like a phosphorus, right? So again, the point is that you don't have to memorize all of these, but you can just sort of look at the type of structures that are there and ask yourselves, are these molecules that would stabilize through withdrawing? Okay. Now, we only got a few minutes left, but again, you should be able to. The point that I'm trying to make is that in both cases where we talk about donors and quote-unquote acceptors, so I guess I got to be careful about the terminology, right? Because it sounds like the book is thinking about it a little bit differently than I am in terms of the terms that are being used. Let's just say orthoparadirectors, instead of calling them donors and acceptors. Orthoparadirectors generally will stabilize that group either through generation of, say, for example, a tertiary carbocation, right? Or resonance, right? So all of these other ones, resonance stabilization, right? So if you have that ability to either stabilize that carbocation through resonance or inductive donating, you'll get either ortho or para, right? In a case in which you have something that can, on the opposite end, stabilize the negative charge, right, then it's going to lead to the meta-directing group. Okay, does that make sense? Okay. Now, to just sort of glaze over some of this previous confusion, hopefully not creating more confusion, the effects of these groups, I think, I don't generally care too much about this, and so I don't spend too much time dwelling on this. The groups, if you're doing electrophilic aromatics, so if you're treating this molecule with an electrophile, right, and you're trying to make those alkenes react as nucleophiles, right, it stands to reason that having, say, for example, a methyl group, right, if we think about our standard right? If we have this reaction, it's almost officially time for me to shock. All right, if we were to react both these compounds with, say, for example, bromine, right? One of these might react a little bit faster than the other, right? And you guys might be able to predict which one and why, right? You would probably say that this one is going to react faster, right? Now, if you said this one because of maybe sterics, that's fine, but it is an electronic argument. And so the idea here is that if you have, if we think about that intermediate, again, I know it's a bromonium as well, but let's just draw that resonance form that shows the positive charge. You have a stabilized carbocation here that's more so than the one that we have over there, right? If we just look at that carbocation, so I know it draws ammonium, but the point is that I just want to show it as that cation to show that stabilization. So the ability to stabilize that carbocation and do a better job of stabilizing that carbocation will make this reaction faster than this reaction. And so as you're reading through your book, what you will find, right, is that oftentimes donors, they'll use this term donor, in the same way that, say, this methyl group donates electrons into the system, makes the reaction faster. And so almost uniformly, when you can stabilize that positive charge through cation stabilization, it will have an effect on accelerating the reaction. So toluene is going to react faster than benzene, right? If you don't have anything there, right? Having that methyl group there will make it be a better nucleophile. An ether, right, is going to be even better than, say, for example, a toluene group, right? Because you'll be better able to stabilize that character, and on and on and on. The one thing that's different, again, I don't generally dwell on this too much, is halogens, right? And this is what was coming up before, is that halogens are technically not considered donors, in part because they undergo electron withdrawing. And so halogens are the rare exception, in which case they slow down the reaction, but it's never really been something that's ever come up in a question that I've ever cared about, so I generally don't worry about it too much. I'm more concerned about you being able to recognize, I don't dwell on the rates too much. I'd rather have you recognize that the resonance leads to orthopara or meta. So again, what we did today, just to summarize, I just want to introduce you guys to aromatic chemistry. We really haven't talked about any specific reactions yet. Right? I just wanted to give you guys an overview of the type of chemistry that we're going to do, which will mostly fall under this category of reactivity. And we'll discuss this next Wednesday. So, all right? Next Wednesday. Next Wednesday, not this Wednesday. We're reviewing this Wednesday. Yeah.